You know, we are surrounded by a kind of secret language every single day, the language of the physical world. It's called 3D geometry. Now, that might sound a little intimidating, but I promise you, you're already fluent. We're just going to learn the grammar.
Just look around you right now. See a can of soda? That's a cylinder. A pair of dice from a board game? Yep, that's a cube. We're literally swimming in these shapes all day long. They're the building blocks of, well, everything. See? I told you. You've already got the intuition for this stuff. Think of this as us finally opening the textbook for a language you've been speaking your whole life. We're just here to finally learn the formal grammar behind it. So here's our game plan. First, we'll get the basic language down so we can actually describe these shapes properly. Then, we're going to learn how to unfold them to measure their skin, and then how to fill them up to measure the space inside. We'll even slice right through them before we put all these new skills into action. All right, let's dive in. Section 1. Seeing in 3 dimensions. This is all about taking that gut feeling you have about shapes and translating it into the powerful, official language of mathematics. You know how you'd call that sharp point on a box a corner point? Well, in math, we call that a vertex. That flat surface, that's a face. And the meeting line where 2 faces come together, that's an edge. It's that simple. We're just giving our words a little upgrade. And once we have these new words, we can uncover this incredible secret code that connects them all. It's called Euler's formula. For pretty much any solid shape you can think of, the number of vertices minus the number of edges plus the number of faces always equals 2. It doesn't matter if it's a cube or a crazy complex crystal. It's a fundamental rule of the universe, which is kind of mind-blowing. Okay, so we've got the language down for describing a shape from the outside. But what if we could, well, flatten it? That's exactly what we're doing in Section 2. We're going to unfold these solids to find their area using the magic of something called nets. The idea is actually super intuitive. Just imagine you have a cardboard box. You carefully snip along a few edges, not all of them, and then you lay it out completely flat on the floor. That flat 2D shape you're left with, that's the box's net. It's like the shape's blueprint. Okay, but why are we doing this? Why bother unfolding imaginary boxes? Well, the area of that flat net is the exact same as the surface area of the 3D shape. It's a hugely powerful tool for just picturing things in your head. And trust me, if you're ever in a math competition, this is a trick you'll see all the time. Let's take a cube. It's the perfect example. When you unfold it, what do you get? Boom, 6 identical squares, all connected. So if you want to find its total surface area, you just find the area of one of those squares and multiply by 6. The formula comes right from the picture. You don't even have to memorize it. All right, so we figured out how to measure the skin of a shape, the wrapping paper, if you will. Now for Section 3, let's talk about what's inside the box. We're tackling the 2 biggest measurements in 3D geometry, surface area and volume. Let's keep things simple. Surface area, which we just looked at, is just the outside. The easiest way to think about it is paint. How much paint would you need to buy to cover every single nook and cranny on the outside of an object? That's its surface area. Volume, on the other hand, is all about the inside. It's about capacity. So it's not the paint on the can, it's how much soda you can pour into the can. How much water could you pour into something until it was completely full? That amount, that's its volume. Okay, but this brings us to a question that trips up almost everybody at some point. When you start looking up volume formulas, you see this weird fraction pop up for pyramids and cones. Why on earth is there a 1/3 in their formulas, but not for things like prisms and cylinders? Believe it or not, the answer is so simple, and it all comes down to this one number, 3. Here's why. It turns out that if you have a prism, you can fill it up perfectly with the contents of exactly 3 pyramids, as long as they all have the same base and height. The same thing works for cylinders and cones. It's a direct physical relationship. So that 1/3 in the formula, it's not random. It's literally telling you that a pyramid is 1/3 the volume of a prism. And once you know that, this table of formula starts to look a whole lot less like a random list to memorize for a test, and a lot more like a logical system. You can literally see the relationship between a prism and a pyramid, right there in the math. So let's do a quick pop quiz. If you take a cube and you double the length of all its sides, what happens to the volume? Does it just double too? You'd think so, right? But nope, the volume actually gets 8 times bigger. It's wild, but it makes perfect sense because you're doubling the length and the width and the height. So that's 2 times 2 times 2. All right, we've explored the outside of a shape and we've explored the inside. Now it's time to level up. What happens if we just slice right through one? Welcome to Section 4, where we're going to talk about cross-sections. This is a classic visualization challenge and a huge deal in math competitions.
The concept of a cross-section is really simple. It's just the 2D shape you see on the inside face after you've made a clean cut through a 3D object. If you slice a loaf of bread, each one of those slices is a cross-section of the loaf.
And here's where it gets really fun. The shape you get totally depends on the angle of your slice. Slice a cylinder straight across its top, you get a circle. But slice it straight down the side, you get a rectangle. And you can even get a perfect hexagon out of a cube if you slice it just right. The only boring one, really, is a sphere. No matter how you slice it, you're always just going to get a circle.
And now for our final section, geometry in action. This is where we put it all together. Our new vocabulary, our knowledge of nets, volume, and cross-sections, the whole shebang. We're going to see how all these pieces let us solve a problem that looks genuinely tricky at first. Okay, check out this classic competition problem. A flat plane cuts a cube, but it slices it through the exact midpoint of 3 edges that all meet up at the same corner. The question is, what's the shape of that cross-section? If you trace the path of the slice on each face of the cube, you'll see it forms 3 equal sides. It's an equilateral triangle. This is exactly where all that practice visualizing pays off.
So we've learned the formulas and the language to calculate the world around us. But the real takeaway here, I think, is something bigger than that. It's about learning to see the hidden structures in everything. So I'll just leave you with this question. Now that you know how to unfold, fill, and slice through the world, how does seeing all these hidden shapes change the way you look at everything? Thanks so much for joining me.